All right. Well, in this video lecture set, we're going to be discussing structural equation modeling, which has a lot of overlap with our confirmatory factor analysis. We're going to start off with some review and then some background, which isn't really review. It's stuff you may have never seen before, but it's also not really the point or topic of this lecture. It's just a couple of things that you'll need to know so that we can continue on with the discussion of structural equation modeling. We'll move into a discussion of the potential of the method, including some limitations. I find that SEM is a pretty buzzwordy type term in the sense that everybody likes to think it can do anything, but sometimes we don't have an intelligent conversation about what are the practical impacts and what are the practical limitations of a method, because any method, no matter how good, isn't perfect and has some things that it is not well suited for. We'll discuss some of the process of structural equation modeling. According to me, there's a lot of different people who have different processes, but we'll discuss what I do. And then we'll work through an example and move into software and see how can this actually be done. So let's jump right in. To start with, let's review confidence intervals for hypothesis testing. So this isn't related to SEM or CFA or any of the fancy methods. This is just plain old classic confidence intervals and plain old classic hypothesis tests. So recall that these are actually theoretically based in the same thing. And really, the confidence interval is just a rearranging of many of the components created and used in the hypothesis test, and vice versa. The hypothesis test is just a rephrasing of different numbers used in the confidence interval. Because of this theoretical alignment, we can actually use confidence intervals for hypothesis testing because, again, it's the same numbers, it's just rearranged a little bit. To do this, we simply check if the null hypothesis value from the confidence interval or from the hypothesis test, excuse me, is in the interval expressed in the confidence interval. If the null hypothesis value from the hypothesis test is in the confidence interval, then there is not a statistically significant difference between our data and the null value. Of course, if the null value is not in the confidence interval, there is a statistically significant difference between what we found and the null hypothesis value. So for example, we can consider a very common one done in regression. We assume that the slope is equal to 0. That is, there's no linear relationship between the independent variable and the dependent variable. We can calculate a confidence interval for that slope, and in this case, we found it to be 0.184 to 2.595. And in comparing the null hypothesis value, beta 1 equals 0, to the confidence interval, we find that that value is not in the confidence interval. And such, there is a statistically significant slope. The slope is statistically significantly greater than 0 at the alpha equals 0.05 level. I should say this is useful and this is possible, but I do want to be clear that confidence intervals and hypothesis tests, while they're the same theoretically, in practice, sometimes they aren't the same. Typically report both of these, but again, we can use confidence intervals for hypothesis tests. So this is something that will come into play potentially later on. All right, so for our first background slide, we're going to talk about path analysis. And again, path analysis background, this isn't something necessarily that you've seen before. Path analysis is actually an extension in some ways of multiple regression. And this allows us to model more complex relationships. So for instance, in like a traditional multiple regression with two independent variables modeling a dependent variable, I can model whether or not I allow the independent variables to be related. So in multiple regression, believe it or not, I know everybody tells you you want your independent variables to be not correlated, and you don't want them to be highly correlated, but they are allowed to correlate. We just want that correlation to be small, but it's not like we're restricting that correlation and demanding it not be there. In path analysis, we can restrict that correlation. We can say there is absolutely no relationship between the independent variables allowed in the model, and we can test that if we want to. So we could actually do some very explicit things in terms of the relationships between independent variables in a model if we want to. Another thing we can do is use dependent variables from one part of an analysis as an independent variable as another part of an analysis, all within the same model. So let's say I'm studying the effect of intelligence on your salary. And what I wanted to do is see, does intelligence directly affect your salary? Or maybe your intelligence affects how well you negotiate, and it's how well you negotiate that actually affects your salary. So, in that hypothesis, intelligence affects how well you negotiate. Well, intelligence is the independent variable, how well you negotiate is the dependent variable. Intelligence affects how well you negotiate. But then I turn around and say, how well you negotiate affects your salary. So, how well you negotiate becomes an independent variable, and salary becomes a dependent variable. In that case, how well you negotiate is both a dependent variable from your intelligence and an independent variable in terms of your salary. So, it's both an independent and dependent variable. And that's kind of what we're saying here is in path analysis, you can do that. What this lets you do then is actually assess something called mediation. So that relationship I described, intelligence impacts salary through how well you negotiate. That's called a mediation. How well you negotiate is a mediating factor in that particular type of model. And because I can draw that and assess that, analyze that inside of a path analysis, that allows me to directly assess a mediation, which isn't possible in standard regression models. Here's the interesting thing though, because of this, um, my old quote unquote dependent variables and quote unquote independent variables, well, I shouldn't say quote unquote, my old dependent and independent variable terminology is not going to be sufficient here because no longer do I have dependent and independent variables. Some variables can be both dependent and independent at the same time. So I need to have a new name for that. So the new names that I have are endogenous and exogenous variables. And we can relate them to dependent variables and independent variables, but they're not exactly the same. So endogenous variables are my former dependent variables for the most part. And what that means is when I'm drawing out the graph, we're going to have some directional arrows. Endogenous variable has an arrow pointing to it. So in one case, we have IQ pointing to how well you negotiate. How well you negotiate is an endogenous variable, and IQ is going to be the other one. No, the other one is exogenous variable, so IQ is going to be exogenous. Those are our former independent variables. Now, what's interesting about exogenous variables is that we say no arrows point to the exogenous variables, with the exception of variance and covariances. So we can have exogenous variables that have variance and covariances, but no directional arrows point to these exogenous variables. If a variable has a arrow pointing to it, it's endogenous. If a variable doesn't have an arrow pointing to it, it's exogenous. And the phrasing for this comes from where the variance associations are coming from. Endogenous, the variance associations are coming from in the model. We believe we're explaining the variance in the model. Exogenous, the variance for the variable is not being explained in the model. It's from outside exo. Now, one big note, epic foreshadowing, is that the path analysis requires all variables to be observed. So I can't do this with latent variables that we talked about in EFA, CFA. I can't do this with factors. I have to have direct observation of all of these in order to be able to do my path analysis. All right. So, hidden paths. We already talked some about hidden paths in the CFA lecture. And that is sometimes there are paths that aren't shown on the diagrams, either in a published lit study or actually sometimes even in Amos, though Amos makes us write a lot of them. Um, This happens the most with error, variance, and disturbance terms. In fact, I'd say this happens only validly with error, variance, and disturbance terms, but we don't have to jump into that. I think we mentioned this in the CFA presentation, but it's worth specifying here because I don't think we talked about exactly what these were. So variance terms, now that we have the terminology exogenous and endogenous, variance terms are used with exogenous variables, our old independent variables. And these represent the movement in the exogenous variable. Error terms are used for unexplained variance in endogenous variables. So if you think about endogenous variables, specifically endogenous observed variables, these are variables that have arrows pointing to them and thus are trying to explain the variance in them. But within these within these endogenous variables, yes, with the arrows pointing to them, there is going to be some variation in the variable that is not explained by the variables who are pointing arrows towards that endogenous variable. And the variance in an outcome that is not explained by all of the things that we are hypothesizing or contributed to it, that variance we call error, typically in regression. So this error term is the unexplained variance in an endogenous variable, that is in a variable with arrows pointing to it. Arrows pointing to it, think about it's an outcome variable. And when the outcome variable has variance that isn't explained by all of the independent variables in the outcome variable, we call that unexplained variance error. So that's basic old regression stuff. And this is true, except now we have endogenous arrows pointing to it, and it's variance that isn't explained by that. Now, the important thing on this particular bullet is that the error terms are for unexplained variance in endogenous observed variables. And I say that because then we have disturbance terms, which is the exact same thing, except it's for endogenous latent variables. So there's a very, very close relationship between error and disturbance, with error being regarding the observed variables and disturbance being regarding the latent variables. Again, we've discussed these within the context of CFA, and we discussed that we can fix these to 1 to give the factor meaning. This is also discussed in your chapter reading. But this last one, the idea of a disturbance term and the distinction between error and disturbance, again, that distinction is both are unexplained variance. Error is just for observed, disturbance is for latent, is important. One thing to remember is that as a rule, all exogenous variables have an error or disturbance, and all exogenous variables have a variance, and all endogenous variables have an error or disturbance. So all of these things are there, even if they're not shown. Exogenous variables have variance, endogenous variables have error or disturbance. All right, so let's jump into kind of the meat of this lecture, and that is the potential of what we can do. Structural equation modeling, SEM, is a combination of path analysis, this kind of regression plus, and confirmatory factor analysis. So let's unpack this a little bit. We have path analysis, which is, for all intents and purposes, regression, but can test some cooler relationships, and confirmatory factor analysis, which is a measure of our measurement instrument, that the survey, how well the items are loading on the pre-specified factors. So combining these lets us test the relationships just like we would in a regular regression. But now, instead of testing relationships between two observed variables, that is, I have direct measurements about them, by incorporating the CFA component, I can test relationships between two latent variables. That is, I can look at multiple regression relationships between two variables that I don't have a direct measurement of. Incidentally, I can do this when I don't have a direct measurement of them while assessing and incorporating how well those variables were measured. So I can do this while assessing and incorporating how well those items fit with that latent variable. And this is a very, very powerful tool because many times in management and psychology and really all the social sciences, What we're trying to assess and what we're trying to look among relationships are, excuse me, what we're trying to look at relationships between are variables that aren't explicitly observable. And in that case, structural equation modeling is very helpful because it lets us use many of our tricks from multiple regression, but it also lets us use these latent variables instead of having to make something explicitly observed, which again often isn't possible in social research. So this improves CFA because it lets us use the latent variables in a way that CFA was just they were there and we were really looking at item loadings. But now in SEM, we can use the latent variables and look at the nature of relationships and if there are relationships between those latent variables. And it's really simple. We just start drawing directional arrows between these latent variables from CFA to start saying, we believe A causes B, or A is the independent variable and B is the dependent variable. So we can start doing regressions pretty much really straight from the CFA just by starting to erase our covariances that we have between all of our latent variables and drawing directional arrows. Now, this is actually very similar to path analysis, but it improves path analysis because path analysis requires everything to be observed. But here we can have latent variables, which are more accurate than just using like an average score because it accounts for the fact that the measurement may not be reliable. It accounts for the item loadings. It accounts for all of this, all within a single structure. So we're not doing one measurement model and one path analysis model separately. We're incorporating all of the errors, all of the statistical power from the measurement model into the path analysis so that we can interpret and analyze it holistically. This video has been a discussion of some of the background of structural equation modeling.